So I got the data in. Let's see. All right. So Dan noticed something very interesting. They're calling the Del Taco bean half-pound pita cheese burrito as a half-a-pound burrito. But then the Google search comes up at 0.53, which is over a half a pound, which is exceptionally close to our sample average. I mean, if you round it off to hundredths of a pound, which hundredths of a pound is probably imperceptible even in small quantities. It's damn close to what they're saying it should be. But then again, 9% is also close to 8%, right? The question is, are they different? Are they arguably different, or are they arguably the same? Is, for example, 0.526 our sample average, which should be close to mu, yeah? That should be close to mu. We know that from the central limit theorem. We get accuracy for free based on my somewhat random sample. And I'm sure some of this stuff is automated. Like, for example, you give them one squeeze of this, or hold this for 2 seconds. I'm sorry, I know. Stace?
I actually know what they do.
Oh, you do?
Yeah, I managed there when they first opened.
Is it fairly automated?
No, they actually make them all by hand, and their beans are made by hand and everything, and they have a scale when you first start working. They have a scale until you get used to making the half-pound burrito.
That's exactly. I used to bartend, and I remember every month we'd go in with a shot glass with a line on it, and we'd practice pouring an ounce and a quarter, which is a shot. We call it a 5 count. 1 second for each quarter ounce, and we'd practice the line. We'd 1, 2, 3, 4, 5. Look, see if it was close, throw it out. We use water. Throw it out.
Drink it.
1, 2, 3. It's funny, as the night went on, it got worse. And then we practiced without the line, and we tested against the line cup. Same exact idea. You're trying to essentially shrink that margin down by increasing your sample size and increasing precision over time. Exactly. Good. So yes, these should be fairly close. Now the question is, knowing that makes me think that the margin that we've got, once we adjust it inferentially using a central limit theorem, is going to shrink down tight enough that we can say to ourselves, okay, right now the sample standard deviation is 0.025 pounds. 0.025 pounds, yes? Now if you take 0.025 and add and subtract that from 0.526...
I was going to say, arguably, I would say that on average, that the weight of the burritos will be between half a pound and that.
Love it!
And that those are your margin of error.
Good! Now don't forget, yes.
Okay.
I love this discussion. We have time to kind of get this started. Yeah, we can see that. What we were just doing last week was estimating little p. And little p was a what? The probability, I like that, proportion, percentage, I mean you can call it anything you want really. But the idea is, if you guys actually quoted it earlier, we could test little p on this one. The percentage of those over a half a pound. Somebody said it's 23 out of 30. We can actually run a 1 prop z int if you want to on this. But the idea, if you run that single proportion confidence interval, that 1 prop z int, as your TI calls it, if you're at 95% confidence, the idea is you take your sample's center p hat, and you add and subtract from that your margin of error.
So could we use a definer?
Say that again.
Could we just find the margin of error?
That's what we have to do right now. Right now we have to find the. Sorry, I didn't say it. Right now we have to find the proper margin of error for our new study. Now here's the problem. We can't use the one we just used before. Do you see why? And you can say no, of course.
Can you say the one we used before?
Yes, I'm going to put it up here mathematically. Now, we're not going to crank these by hand, this one by hand anymore. You've already done it once, that was enough. But the margin of error was a critical value, z, usually 2, 1.96 or 2, times a standard error, which was p hat, q hat over n. Now, if you look at this, some of that we know from this study, ish. For example, we know what n is, and 30. And we know what, we don't know what p hat is. Well, I mean, over here somebody said 7%, 7 of 30 were below half a pound. But that's the percentage of those below half a pound. What we just got done, which is now off the screen though, what we just got done analyzing wasn't the percentage under half a pound, but it was, say that again, the actual average weight. So the trick is, we can't use this margin of error because this is tied to percentages. We need a way to estimate an average, which we call mu. And you have to say it that way in this class, I'm sorry. It's not just mu anymore. No, we have to, mu is out there. The average weight of a Del Taco half-pound beef and cheese burrito is out there somewhere. Our job is to figure out what it is within confidence limits. So what we have to do is we have to run something which we will get to eventually. I want to do the first one manually because I want you to see the derivation of what we're going to be doing. There's some history behind it, which is actually kind of cool. But the same idea. We're going to start with the center of our sample, but it's not going to be p hat. It's going to be, say that again? No, for averaging, what's this? X bar. That's the corollary, X bar, because it's an average. The reason we went to p hat with little p was because that's the population proportion. This is the sample proportion. This is the population average. So we have to take our sample average, which we called X bar back. I know we got away from using X bar at the end of 243 because we were into distributions and we're talking about mu all the time. That's why I like this class. It brings back X bar. So X bar plus or minus the margin of error. And the question is, how does the margin of error differ for a population average versus a population proportion? Let's get some ideas up before we take our break. How is it going to have to differ? What do you think is going to be included in it? Let me turn this back on. There's what we just crunched, like our Del Taco results. What do you think is going to have to be included in the margin of error? Ideas, anything. Be brave, I'm hearing it, I'm beginning of it.
Standard deviation.
Yes! Absolutely! We're going to have to use this sample standard deviation. Because, now, thanks, it's awesome, JC. You have to remember, back here, this one for proportions, the standard deviation is in there. The P times the Q, I don't know how many of you got a chance to watch the video that showed you the derivation of this thing, but it starts with the standard deviation of the binomial, and then it is transformed into this. So yeah, we definitely have to start with S. That's going to be part of it. Absolutely. Fantastic. What else should be a part of that, do you think? And you can actually use this one as a model. You can use this one as a model to kind of look at this one. They're similar. They're not the same, but they're similar. Go ahead, be brave. Yes! Your sample size. Why is your sample size important? I'm going to do this in red. Say that again. Is that you, Dawn? Go.
No.
Go. Megan. JC. All of you. Go ahead, JC.
How we got our average.
Excellent. And what happens with sample sizes? We learned this at the end of 243. We've kind of been seeing it the first couple weeks here.
The bigger the better.
Bigger the better. Well, wait. Thank you.
More precision.
Yes! The bigger the better, more precision. Now, the standard deviation itself isn't going to vary very much based on sample size. It might actually get worse as your sample gets bigger. But the inferential standard error, which is where the margin of error starts from, has to get more precise as your sample goes. And the limit theorem guarantees us that. So what are we going to divide this bad boy by? What do you think? Root n. That's the part you might forget from central limit theorem, and that's okay. It's going to be the square root of n. That's the result, and Kate brought up a very good point. It's one of the last things we do in 243. It probably has slipped your mind by now. But do you notice over here, you've got an n, but it's under a square root. So the root of n is present here. It's also present over there. What's the only piece missing? That is now a standard error. Yay! And we can be done right now. We can be done right now as long as we're happy being how confident? Not very. Give me a number. Be brave, you know this. 68%. Right? That's one standard error.
Gotcha.
68%.
So you gotta put your Z or 1.96.
Good! Now here's the catch, and we don't have time to do it before the break, but after the break. It's actually not a Z.
Oh, okay.
It's something else, and I don't want to explain that in 30 seconds. Let's come back and learn a little bit of history of statistics and figure out what needs to be. Yes, it has to be a multiplier, and it has to be something, some number, some numerical value. Let's come back to it. Take your 5, get some air, get some water, and we'll a little bit of history. It has to do with the Guinness Brewery. It might be interesting.